Okay, so in the previous video we saw some examples of using the sine rule. Now in this one I want to talk about the proof of this. So how do we show this is always true for any angles A, B and C and lengths A, B and C? Now the way we do this, well, we see that we have sines in here, so let's first remember what the definition of sine is. If you have a right angled triangle, then sine of the angle x, this is the ratio of the opposite side divided by the hypotenuse. So if we just have a little triangle like this, and this is our angle x, this is the opposite side, and this is our hypotenuse. So this is the definition of sine, but to use sine we need a right angled triangle. So this has to be 90 degrees. So we want to find expressions for sine of A and sine of B, but to do that we need a right angled triangle. So we're going to use a little trick. We're going to drop down this line here. I'm going to draw this dotted line all the way down. So we create two triangles, and these are both now right angled triangles. And I'm just going to label the length of this line h. So now we have a right angled triangle with this angle A, which means we can write what sine of A is using this definition. So sine of the angle A is the ratio of the opposite side divided by the hypotenuse. So here the opposite side is this one, which has length h. So we have h divided by the length of the hypotenuse, and the hypotenuse is the longest side, so it's this one, it's b. So sine of A equals h over b. And we don't know what h is, but what we can do is we can rearrange to get it in terms of h. So I'm just going to bring up the b, and we have h equals b times sine of A. And now our plan is to find another expression for b, sine of b, and then we can eliminate h. So to find sine of b, it's kind of a similar strategy. We now look at this right angled triangle, the one on the right. So this is also 90 degrees, and we can just use this definition. So the ratio of the opposite length to the hypotenuse, the opposite is again h, but now the hypotenuse isn't b, it's actually this length, the longest side of this small triangle. And this is a, so we have h divided by a. And again we can rearrange to get in terms of h, so h equals a times sine of b. And this is really nice because we have two equations for h, and so we can equate them because they're going to be equal because they're both equal to h. So this tells us we can deduce that b sine A it equals h, so it also equals this stuff, it equals a times sine of b. And you can see we're almost there. What we do is we divide by a. Actually, we want to divide by sine of a and sine of b. And then we're going to be left with b divided by sine of b. If I divide by this, and then this equals a divided by this. So if I divide by sine of a divided by sine of a. And this is exactly the sine rule. So we just showed this first equality, but the second one follows just by relabeling all the points. So I'm not going to do it here, but if you just draw the vertical line in a different vertex, then you can show this equality as well. But it's the same strategy essentially. So let's just recap what we've done. So we're trying to show this equation is true, and to do that we looked at the definition of sine, which is the length of the opposite length divided by the hypotenuse if we're working in a right angled triangle. So we created two right angled triangles, and then we wrote the definition of sine of A and sine of B in terms of these new triangles and in terms of h. Then we rearranged for h and equated these two equations because they're both equal to h. And this is how we got the equation involving sine of A and sine of B. And if we just did a bit of rearranging, this actually gave us our result. So it's a bit complicated, just make sure, go for it a couple of times, make sure you understand it, but this is the strategy to proving this. So this is our proof.